I see the camera.
Okay, hi everyone. Welcome to Compass Seminar, Compass Wednesday Seminar. As a reminder, this is being recorded for YouTube, so it's going to be great today, and you can watch it every day after it's posted. So today we have Dr. Jeremy Klavans speaking to us. He's an assistant scientist here at the Rosenstiel School. He's working with Dr. Amy Clement. He's been a Kane for a while. He did his undergrad here in environmental science and policy. Then he went off to the University of Chicago, where he got a master's degree in public policy, in environmental science and policy. So, a sort of jack of all trades here. And then he came back, did his PhD here in the MPO program, also with Amy Clement. Then he left again, was a postdoc at UC Boulder, but then couldn't stay away, came back, and is now an assistant scientist here. A fun fact about Jeremy is that with all of this back and forth through Miami, before he started on his science career, he was actually a penguin wrangler as a high school intern. So ask him about that during questions later. Up to you. Over to you, Jeremy.
Thank you. And thank you, Mary Beth, for that nice introduction. Mary Beth is no stranger to animals. In her talk last week, I saw a picture of her with a pig as part of her personal theory. Is that your pig? Yes? Awesome. That's really cool. So I was inspired to start with a little story of my own. It's not as fun as Mary Beth's pig. I don't have any mysterious farm animals. But I do have a story of the first AGU that I attended as a PhD student. So as a PhD student and today, my research focuses on regional and decadal climate variability. And when I was starting in the field, I think the dominant view of regional decadal climate variability is that it's primarily internally generated, that the atmosphere-ocean system kind of randomly varies and produces this decadal climate variability. And because it's internally generated on long lead times, it's primarily unpredictable. And at the time, I think state-of-the-art climate models generally confirmed this point of view. And so I want to show you all a picture from the first AGU meeting, from a talk at the first AGU meeting that really stuck out to me and has stuck with me for the last too many years. And it seems to show that climate models are validating this idea that regional decadal variability is primarily internal. And I think this picture also provides some good context for the work we're going to share today, including some of the methods that we're going to use. So these are maps of North American temperature trends from 1963 to 2012 from 12 different models, or 12 different ensemble members of the CESM1 large ensemble. Surface air temperature is in the colors there, and the contours are sea level pressure. As you can see, each of these simulations are pretty different from one another. So you can find simulations, get my fishing pole now, where there's cooling in northern Canada and warming in the southeast US. You can find the opposite simulation too, where there's warming in northern Canada and cooling in the southeast US. So if each of these runs of the same climate model are supposed to be some sort of counterfactual climate, it shows us that the last 50 years could have played out very differently. If we take this at face value, it says that the climate is a pretty normal or pretty noisy system, at least on these regional and decadal spatial and time scales. So just for introduction, what makes each of these maps so different, each of these ensemble members so different? Each of these runs has the same physics. They're run with the same model, so they have the same physics of the atmosphere, ocean, land processes, and sea ice. And each of these model runs experience the same boundary conditions. We're primarily concerned with the evolving time history of greenhouse gases, industrial aerosols, as well as volcanic forcing. But each of these model runs start from slightly different initial conditions. And as you all know, the climate is a chaotic system, so minute perturbations and initial conditions lead us to very different time histories of internal variability in these runs. And that's what this large ensemble of all these model runs was designed to do, was to kind of subsample this range of potential internal variability and show us the different ways that the last 50 years could have played out. Just trying to advance slides here. There we go. All right, and here's the rest of that 30-member ensemble at the time, just for completeness. This was a pretty big ensemble at the time. And I'm comparing that ensemble to observations that's on the right-hand side in the big plot there. So as you can see, first, many of these runs are very different from each other. And second, many of these runs are very different from observations. If you squint at all those little postage stamps, which I made very small on the screen, you can find a member or two that kind of looks like observations. I think this one, number 7 up here, kind of looks a little bit like the observed map. I think that's pretty reasonable, and that was enough for these ensembles to be considered a success. Observations fell somewhere in this range of what the models could produce. We didn't know what internal variability should have looked like, so as long as it's somewhere in this distribution that the models are producing, then we can't show that these ensembles are doing anything, or that the models are doing anything wrong. Observations could be a random draw from this anywhere in the distribution. And so that argument for why the models were doing okay is based on that assumption I mentioned earlier, which is most regional decadal climate variability is internally generated. I think that was the dominant view in the literature. I think it mostly still is in the IPCC reports, other governmental reports. But from a predictability standpoint, and that's kind of something else I work on, it's related, I think that's a pretty pessimistic attitude. It suggests that regional climate becomes inherently unpredictable on longer timescales. And I don't really like that for my work. It says that there's not too much that we can be working on at longer timescales. And I think predicting regional climate is pretty important. I know a lot of you work on the same type of things, maybe different variables or different components of the climate system. But something about these plots, something about this presentation from 10 years ago or whatever, has stuck with me, but looking back on it, there was something that was a little at odds with that assumption. And that is, if you took the average of all those maps, you get something that looks really similar to observations. And that's what's now plotted on the right-hand side, the average of all those little postage stamps. So what is that average, physically speaking? Well, to state the obvious, it's the average, it's what's in common for each of these ensemble members. I already mentioned that each of these model runs have the same physics, they experience the same boundary conditions. So when we average over all of the internal variability that we see at all the postage stamps, we're left with the common model response to external forcing. So this is the forced response, the model's response to things like greenhouse gases, industrial aerosols, over the last 50 years. What's interesting about this ensemble mean, that's what I'm going to call that average, as opposed to all the internal variability, is that external forcing is reasonably predictable, at least on the timescales of energy infrastructure right now. So if we know something about the greenhouse gases that we've emitted over the last few years, we can make a pretty good guess about what's going to happen next year and the year after that. So maybe their climate system, or regional and decadal climate, is a little bit more predictable than was previously assumed. And that's what I'm going to argue today. That regional climate on decadal timescales is much more predictable than previously thought via its externally forced component. And the reason we didn't see it sooner is because there's an error in climate models. So in climate models, the forced signal, I think, is too small relative to all that internally generated noise that you see on the maps at the left. The incorrect forced signal to internally generated noise ratio, the signal to noise ratio in climate models, is too small. And it's been obscuring the predictive power that models have for regional climate. And so we're going to try and better understand this predictable component in a few different regions through the lens of 3 major climate modes. Some of you may be familiar with them, but I will give a very quick background, I promise, to try not to bore you. on these three modes that I'm going to use, including their impacts and mechanisms. And then I'm going to start trying to convince you that everything I just said now is somewhat right, that there's a significant role for external forcing in these regional climate modes and their impacts. And I'm going to do this by doing a deep dive first into one specific mode, the Pacific Decadal Oscillation, or PDO, and then we're going to see if we can generalize this beyond the North Pacific in the hopes of showing that this is a pervasive problem in climate models, at least in the extratropics. And if this is a pervasive problem, it has pretty big implications for our ability to predict regional climate. That is, if there's a large force component in regional climate modes, these modes are much more predictable than previously thought. And so, as an example of this, I'm going to try and make a prediction for you all, and then we can all meet back in like 10, 15 years and see if my talk was any good. I'll conclude by offering some next steps in how we should be thinking about climate models in light of this error, and how we can be mitigating and improving the signal-to-noise error in climate models. So let's get started. First, what do I mean by regional climate mode, in case there's anybody who doesn't love all of these acronyms. This is just a spatial pattern of a climate variable with societal interest, like temperature or pressure, paired with a fluctuating time series that summarizes a key feature of regional climate. So it's just a shorthand, a description of something happening in one region that lets someone like me understand it instead of trying to dive through a whole bunch of variables. So my examples are going to be the AMV, or Atlantic Multidecadal Variability. You may have heard this referred to as the AMO, or Atlantic Multidecadal Oscillation. I'm just going to call it the AMV. It describes how sea surface temperatures vary in the North Atlantic after removing a linear trend to account for the global warming signal. So this is just a basin-wide average of SSTs in the North Atlantic. Here in the time series, you can see that there are decadal fluctuations about that warming trend. If you regress SSTs onto that time series, you get the spatial pattern on the right. So that's the pattern in which these temperatures go up and down. And this pattern is associated with impacts like the number of hurricanes that form in the Atlantic, as well as precipitation in the Sahel or the southeastern US, and even here in Florida. The AMV is primarily thought to be caused by variations in the large-scale ocean circulation, especially AMOC, the Atlantic Meridional Overturning Circulation, with potentially some role for the overlying atmospheric circulation. The kind of key point that I'd like to make about this is all of those mechanisms are thought to be internal to the climate system. So people generally think the AMV, or thought the AMV, was primarily internally generated. So the second mode I'm going to talk about is the North Atlantic Oscillation. This is the first mode of sea level pressure over the North Atlantic. You can again see that there's decadal variability even through all that weather noise. You can kind of see it going up and down in the time series there. You can regress sea level pressure on it. You get a pattern again of what that looks like. The North Atlantic Oscillation is particularly important for weather and regional climate in Europe. The NAO is primarily thought, at least my read of the literature, to just be stochastic variations in sea level pressure that we're capturing with that first EOF, or you can use a kind of station-based index, which is what I'm showing here, the difference in sea level pressure between Iceland and Portugal. So again, the main point is that most people think that the NAO is a stochastic mode of variability generated by random fluctuations in the atmosphere. And then finally, the one I'm going to talk about most today is the Pacific Decadal Oscillation, the PDO. I'm defining this as the first principal component of SST in the North Pacific after removing the global mean temperature signal. Like for the NAO and AMV, we can see the decadal variations in the time series, so we're talking about real kind of decadal variability here. And then we can see its pattern on the left. That's the positive phase of the PDO, where we have cooling in the western and central North Pacific, and then that characteristic horseshoe of warming along the coast of North America. The PDO is associated with impacts that affect people, particularly kind of fisheries in the North Pacific, as well as precipitation in Alaska and the southwest US. The PDO is primarily thought to be generated by a combination of several processes, including an influence from the tropical Pacific, from ENSO, stochastic variations in the Aleutian low, so again, random atmospheric variability, and maybe some contribution from ocean dynamics, particularly along the western boundary current or the current system that sits there. You'll notice again, those are all natural processes that are kind of varying randomly to produce this decadal variability. That's the kind of, I think, leading explanation for why the PDO changes when it does. And so let's look deeper at the PDO. And to do this, we're going to look at a whole bunch of model runs from 12 different models. These are all coming from CMIP5 and CMIP6. We have 572 total ensemble members that we're going to use. These are all historically forced runs, which just means they use the full time history of greenhouse gases and aerosols, our best estimates of that, to force the model. We run it over and over again with slightly different conditions across different models. We're also going to use large ensembles of single forcing runs. Those are exactly what they sound like. Instead of letting every single forcing vary across these runs, like greenhouse gases and industrial aerosols and volcanic forcing, we're just going to let one vary at a time while we hold the others constant. I already defined the PDO index, but the definition's up there on the screen. To calculate the ensemble mean, we'll take the PDO index from each individual ensemble member and average those indices. To get the spatial pattern, we'll take that ensemble mean PDO index and regress SST back on it. And then just for housekeeping, the observations that I'm going to show in this presentation are SST from HADA SST and sea level pressure from the 20th century reanalysis.
Just to clarify,
yeah.
Is that the index from the observations? You're
So-
projecting models onto the observed first PC?
No, so we'll do those separately. We'll calculate the first PC in observations, just from observations, and then in each individual ensemble member, we'll treat them the same as if they were observations.
I see. So then you have different PDOs for every not only every model, but every ensemble member has its own thing you call the PDO.
Yes, they do. The spatial pattern is reasonable compared to observations, broadly looks similar in individual ensemble members, and then I'll show the picture of the ensemble mean. I think in CMIP6, the PDO looks a lot like the real PDO. That is, if you were to like bootstrap observations, look at like 30-year chunks, and then look at where the spatial correlations fall from each individual ensemble member, we're doing a pretty good job. There's a paper that looks at that, the John Fussolo paper.
Sorry? So, okay. If somebody has a question online, you can ask too. Is that good? Okay. So let's go ahead and take a look. And at first glance, we see the same thing that everybody else had, which is that the ensemble mean, which is in that dark blue line there, has very little amplitude. It's really not showing us anything. So that's the end of the talk. I'll see you guys later. No, it does seem like if you squint really hard at that, there is some structure in the ensemble mean in the blues compared to observations, which are in the black. So I'm going to go ahead and amplify that so that observations in the ensemble mean have the same variance. And now we can see that at least on decadal time scales, the ensemble mean PDO, that's in the light blue now that I've amplified it a bit just for visual effect, has a similar structure to observations. The ensemble mean reproduces that positive trend from 1950 to the late 80s and then the negative trend thereafter. It reproduces the transition from negative to positive around 1970 or so, and then reproduces that transition in the 90s again. Again, large scale, kind of broadly speaking, there's some structure there that seems to match observations that's at least interesting and at least we should look a little closer at. So on multidecadal timescales, so using this low-pass filtered data, the ensemble mean PDO explains 53% of the observed PDO time series. That's a correlation coefficient of a little over 0.7. That is statistically significant by tests that account for the autocorrelation in these low-pass filtered time series. I'd be happy to talk about that more if you have any questions.
And so statistical significance is one way of testing that null hypothesis that this correlation could have happened by chance. But another way to do that is to use the output from climate models themselves. Also, it's appealing because they make better pictures. So here what we're doing is testing the hypothesis that the null hypothesis that the large correlation between observations and the ensemble mean could have been reproduced by chance by internal variability alone. So the plot on the right just shows a histogram of the correlation between the model's internally generated PDO and observations. So in each ensemble member, we take the PDO index, we subtract the ensemble mean, that's without any of the variance adjustment or anything like that, just for the plot on the screen. We subtract the ensemble mean, we get an internal only PDO. We correlate that with observations, we do it 500 and whatever times, and we make that distribution. The black vertical line is the correlation between observations and the ensemble mean. You can see that the forced PDO explains more variance than internal variability does by chance at equivalent to the 99% confidence interval, or confidence level. So I think there are two ways that you could interpret this result. The first is the pessimistic view that over the last 75 years or so, we live in a very, very unlikely world, that this is a 99th percentile event. That's if you live in the Southwest and you've experienced drought, which is associated with the PDO, that this is a very unlucky turn of events for us. Or the second interpretation, which I take, is that the black line is statistically distinct from the blue distribution. That forcing is playing a role in the PDO beyond what we'd expect just from internal variability. So how did we find this force signal? Just by correlating a couple things. There's nothing fancy happening here. When so much of the existing literature, when the IPCC reports, when the review papers all say that internal variability is the source of PDO variance. Well, it turns out you need a whole lot of ensemble members to isolate the forced component of the PDO in climate models. And that's because, recall from that earlier time series, that first one I showed with the dark blue line, that the forced PDO has a small amplitude. So by putting all 500 plus ensemble members together, we can see, we can finally isolate that small amplitude forced PDO. And we can see how many ensemble members you would need to isolate that by looking at the plot here. So here, the y-axis is explained variance, so just the correlation squared. And for each value on the x-axis here is ensemble size. So for each value on the x-axis, we're randomly choosing that many ensemble members to make a new ensemble. We're just bootstrapping here. Make a new ensemble, we're calculating the ensemble mean, we're correlating with that observation, correlating that with observations, and then we're doing that 10,000 times to make the cloud that you see in the background, and then we're highlighting the mean of that in the blue dot. We're doing that with ensembles starting at 1, so randomly selecting an ensemble member, out to 500 member ensembles. And as you can see, as you increase ensemble size, the correlation goes up. And it takes at least 100 members or so for that correlation to start to stabilize. And you even have to go beyond 100 members to, I think, get a real good estimate of the force component there. So what does that mean? It means that it needs at least 100 members, at least maybe 200 members, to start to average over all of that really exuberant internal variability that we saw on the postage stamps, those maps at the beginning of my presentation. That to get past all of that internal variability and see what's happening, you need a whole lot of ensemble members. Why does it take so many members? I think that's the best question we have here. It's because there's a lot of internal noise relative to this force variability in the models. And so here I'm going to argue now that it is taking too much averaging to get to this force signal, that the signal to noise ratio is too low. So the red curve here is the same as the previous plot. I'm sorry for the change in colors, it's just a different paper. And as a reminder, that's a bootstrap correlation between the ensemble mean and observations. So that's roughly the forced component in observations. We can do the same thing, but instead of using observations as our target time series, we can use an individual ensemble member. And this will help us estimate what is the forced component in the model. And so that's what we're plotting in the blue line here. So you can interpret this red line as the forced component in observations and the blue line as the forced component in models. For a perfect model, those two lines should be right next to each other or overlapping. They are not. We clearly don't have a perfect model. As you can see, the force component in models is much smaller than our estimate of the force component in observations. And for those of you in the predictability space, this is related to a phenomenon there called the signal-to-noise paradox. They find it curious that models are better able to reproduce observations than they're able to reproduce themselves. If you have any questions about the relationship between that work and this work, I'm happy to talk about it. But hopefully I've at least interested you in the idea that maybe there's a force component in the PDO. And so I want to kind of go back to Brian's question just a little bit and make sure this is really something that looks kind of like the PDO. And I think it has broadly similar characteristics. So the observed PDO pattern is on the left here. You can see it's pretty similar to the map I showed from one of the review papers earlier. And then the ensemble mean PDO is on the right. You see they both have good cooling. This is the positive phase. They both have good cooling in the western and central North Pacific. And then there's that horseshoe shape of warming around it. Now, models definitely have a weaker horseshoe of warming than observations. I think that's interesting. And if you want to talk about it more, I think it may give us a little bit of a clue as to why the forced amplitude in models is too weak. Also note that models and observations are both associated with a deepening of the elution low, but that in models, there's a weaker elution low response. Again, I think that may offer us some clues as to what is happening that is giving models the wrong signal-to-noise ratio. So if you buy the kind of cursory argument here that we think external forcing can explain about half of PDO variance over the last 75 years, what's doing the forcing? I don't think the answer is going to surprise anyone. This is just a summary plot of kind of what we're looking at. We can answer this by looking at those single forcing large ensembles. Again, those are those runs run with just time varying greenhouse gases or just time varying industrial aerosols. This is just a bar chart of the R squared, the explained variance for 3 different time periods. I have 1950 to 1989, which is that positive trend in the PDO, then after 1990, that negative trend in the PDO, and then the last bar in each group is the full time series. Each cluster is a different set of experiments, so we have the all forcing runs in case you can't read the bottom. On the left-hand side, then aerosol only runs, then greenhouse gas only runs, and natural only runs. So the yellow bar, the early part of the time series where we have the positive trend in the PDO, really like having this fishing pole back, this is great. Where we have the positive trend in the PDO, the aerosol only runs do a reasonable job of explaining that trend, and they don't do too much after that. In the later part where we have the negative trend in the PDO, the greenhouse gas only runs are explaining what's happening. There were also quite a few volcanic eruptions between 1950 and 1990 or so. So it may be that natural forcings are helping to explain some of that cool phase of the PDO. But overall, I think that kind of the interplay of industrial aerosols and greenhouse gases, where we have rising aerosol concentrations, followed by a stabilization of aerosol concentrations or some abatement, paired with rising greenhouse gas concentrations, are driving the shape that we've seen in the PDO. But as we mentioned earlier, that force component that we're talking about has been hidden by an unrealistic signal-to-noise ratio. And so I know that was kind of a quick overview of some of our PDO work, so I'll stop or pause here for a second just to see if there's
any questions about the PDO stuff before I keep going in other directions? All right. Yes?
Okay, well, bye. So I'm assuming you use the coupled CMIP6 and CMIP5?
Yes.
I'm curious as to what the pattern of warming may have influenced these results, given that the coupled models have a dramatically different warming trend, especially in the Pacific, as compared to the observations.
So that's a good question. We've done a few comparisons, and I can skip to a slide here if I have it. Yes. So we can look at a little bit of an answer to your question, and then I'll try and jump back to another part of it, which is we did a little bit of sensitivity testing to this. So if you think that like the higher ECS and CMIP6 models may be influencing this, it looks like both CMIP5 and CMIP6 were explaining for external forcing, is explaining a statistically significant portion of PDO variance. Those are the two bars on the left there. You also may think that by imposing aerosol concentrations on the model, we're accidentally leaving in the spatial pattern associated with like winds with the PDO. But there doesn't seem to be a difference between emissions-driven models or those models that are driven with prescribed aerosol concentrations too much. And if anything, the models with prescribed aerosol concentrations have a weaker forced PDO. So that doesn't quite mesh with that hypothesis. And then if you think that it's aerosol cloud interactions, there doesn't seem to be a huge difference between those models with interactive or not interactive aerosols. As far as North Pacific trends, I think you could, I'm not quite sure here, but I think you could also make the argument that the stronger forced PDO is actually changing overall. The PDO is big, the Pacific's really big, is changing overall warming trends across the North Pacific and across the North Atlantic. So depending on how that PDO is represented in models, you may be changing the warming trend itself. So I think that can go both directions. Just kind of depends how the model's responding to warming. Does that answer your question a little bit?
I think so, but I'm just curious because like there's an atmosphere-only subset of the CMIP6 that was created solely to test more or less what happens when you impose the actual SST trends on the models. And the problem, at least I've seen with all the couples models, is that none of them actually replicate that same pattern of warming at the sea surface.
Yeah, that's right. And I think that is exactly what we're arguing here, which is that any individual model simulation, the forced PDO is extremely weak. So in observations, if you were to look at sea surface temperature trends in observations since 1990, so the last 30 years or so, 35 years, getting old, that you would see that negative PDO or negative IPO spatial pattern in the North Pacific. Models rarely do that. They kind of bounce around all over the place, just depending on what the PDO happened to do in that individual ensemble member. So if your interpretation of observations was that the PDO or IPO is internally generated, that would be expected. You wouldn't expect the model's sea surface temperature pattern to match observations. Here we're arguing that those individual models should actually much more frequently look like observations because there's a larger force component there. If you do an AMIP run where you impose observed SSTs, you do a much better job, as I'm sure you know, in getting impacts. Putting the right SSTs make your models more realistic, of course. But we do also see a signal to noise problem in the elution low, where even with the right SSTs, then you think you'd do a much better job of getting the overlying atmospheric circulation. You still have to average over a ton of those AMIP runs to get something like the observed elution low, the strength of the elution low there, or precipitation in the western US. Yeah.
A question about the aerosol emissions. So those are mostly volcanic eruptions between 1950 and 1980.
So there's volcanic eruptions, and then there's industrial aerosols too that are imposed in the model.
Do you see a sensitivity to the location of the anthropogenic portion, like East Asia has been industrializing, Europe has...
That's a good
It
question.
might have been more stable, I don't remember.
It seems to match, at least for the PDO, it seems to match the total aerosol concentration of the northern hemisphere. So if you look at other model runs that are outside of the 20th century, anywhere you impose forcing, so whether it's something like aerosols or if you change vegetation, we did some runs where we changed Siberian vegetation or changed Sahara vegetation, looking back in time, anywhere you impose forcing in the northern hemisphere, if it's large enough, will excite a PDO-like response. So it doesn't seem to matter too much the location of the aerosols, as long as it does a good enough job of warming or cooling northern hemisphere land. So we looked into that. I still think that's an open question. I'm not totally satisfied with that answer. I would like a little bit more of a local response, and maybe it's just the way that the time series of aerosols lining up with greenhouse gas concentrations too. So I think there's more work we need to do there, but that's at least what we've seen so far. Yeah.
How much of the external forcing on the PDO do you think is an artifact of how the PDO is computed from the EOF and moving the mean versus if this external forcing playing such a large role is apparent in other modes like ENSO?
Good question. So the first one is our definition of the PDO, kind of drawing this out of the forcing. If you take a simpler definition of just KOE SST or KOE SST relative to the rest of the North Pacific, dropping the EOF completely, you get the same results as this. Forcing is explaining about 50% of North Pacific variability after removing that warming signal. If you just look at the KOE side, it's a lot higher. It's more like 80%. And then it's that horseshoe pattern that's kind of dragging it down. So we think that it's robust to the definition that we're choosing for the PDO. What was your second question?
If you find this external forcing being a large player in other climate modes?
Great question. So is this a widespread problem in models? Yes, I think we find that external forcing is playing a widespread role in other decadal climate modes throughout at least the rest of the northern hemisphere. And then there's also evidence that forcing is important for southern hemispheric modes like the southern annular mode. It's just the forcing there is a little bit different because you have ozone forcing. So here I'm looking at the two other climate modes I mentioned at the beginning of the talk, the AMV and the NAO. I made this slide while Mary Beth was asking her question. And so here we have observations in the red and the ensemble mean from a large ensemble of CMIP 5 and 6 models. In the blue, the correlation between the ensemble mean and observations over the last 75 years or so is, what would I say, 0.9 for the AMV and about 0.6 for the NAO. I will note for the NAO that that correlation is much higher if you start after 1960, which is giving us some confidence in that correlation. So that means the ensemble mean is explaining about 80% of the variance in the AMV. The consensus a few years ago, I think, was that the AMV was an internally driven mode. I think we've made some progress on that in the literature in saying that there's a force component here. And same for the NAO, which again, after 1960, those correlations go up closer to 0.7, so we're looking close to 50% of the atmospheric variability in the North Atlantic. As a total aside, maybe Mary Beth knew this, this is basically my dissertation distilled into one slide.
which is really humbling. And so if you have any questions about it, please feel free to ask. So anyway, I think there's a big force component in these other modes too. Thank you for asking. I don't want to go too deep into this. If there's any other questions, then I'm just skipping to make jokes for Mary Beth. No, you can stop me at any time, please. So, like the previous plot with the PDO, I think these large correlations are unlikely to be from internal variability alone. Here, the red lines are the ensemble mean correlation with observations, and the gray distributions are the internal only versions of each of these modes taken from the large ensemble that we're using, correlating them with observations. Again, this is testing the null hypothesis that internal variability could have created these correlations. I think we can reject that null hypothesis for the most part based on these pictures and some other statistical tests. Further, if you think that these modes are completely internal and independent of one another, then these two histograms combined with the histogram I showed of the PDO from earlier, that if you wanted to make the case that these modes are varying naturally over the last 75 years or so, you'd have to believe that all these things, these very unlikely results are happening at the same time. So I think that's a little bit more evidence for that there's some force component here that's pushing those red lines out there. So, like for the PDO, not only is the force signal a much more important part of each of these modes than we previously thought, there's also a signal to noise error in each of these modes. You can see that by comparing the red line to the blue line. So a reminder that the red line is the force component of observations and the blue line is the force component in models. Now there's something interesting on this slide here too, which is that the signal to noise error in the NAO appears to be much worse than for the AMV. And across all three modes, the NAO is kind of the worst, the PDO sits somewhere in the middle, and then the AMV after that. So that gives us maybe some clues as to where the source of this error is. It seems like the atmospheric modes kind of have the worst error. The PDO, which is a kind of an atmosphere and SST mode, because of that horseshoe sits somewhere in the middle, and that for SST modes, there's a little bit of a problem. It's not so bad. We can see through it by just using a few ensemble members. I'm happy to talk more about those, what we think are the sources of that error later.
Hey, Jared.
Yeah, sure.
So for that figure, that I'm not sure I understand the red line, because that's the mean, but you have the ensemble. So you average different ensemble.
Yeah, so we take
different number of ensemble members.
Yeah, that's exactly
But
right.
shouldn't be the same value for one?
So we randomly select, take a ensemble size of 100. We take our 500 and whatever members, we randomly select 100 members to
but
create a new
like you
ensemble.
start from one member, right?
Yeah, so we randomly select one member at a
So
time.
the
one
mean
member
would be
at a
the
time.
same as one member, right? If you average one member, that would be just the member.
Yes.
So
for
the
one,
initial
that
value
is-
should be the same
for
both curves.
For one,
The
yes.
correlation coefficient, they should start from the same point and then diverge, right?
Yeah, that's right. So I'm starting at a value of 2 here.
Oh, okay, all right. That's good.
Yeah, that's right. Good catch. Because that value of 1 is all over the place. It's 0.95 to negative 0.95 in correlation space. So
Okay.
It makes it pretty graphically unappealing, and then you have to include the negative 1, and it changes no matter how you set your seed. So it doesn't tell us too much. But good question. So here, just another little summary plot. This is the signal to noise ratio in observations in the red bars and in models in the blue bars. Outlined in black are the 3 modes that I've talked about already today. And then outlined in orange, orange, are some impacts associated mostly with the AMV. So VWS stands for vertical wind shear over the main development region in the North Atlantic, where hurricanes form.
and SRF stands for Sahel rainfall. So that's an AMV impact. So we're curious, okay, if there's a signal-to-noise error in these modes, is there also an error in their impacts? Is this going to give us an opportunity to predict these impacts? That's what we're kind of after all of this work. And so I think we can see that there's also a signal-to-noise error in these impacts, where in observations there's a reasonably high signal-to-noise ratio, but we're not seeing that in models. So if this signal-to-noise error does propagate into impacts, which I think it does, then like the modes, these impacts should be more predictable as well. And so I wanted to give you an example of a key impact associated with the PDO, going back to our big example of the PDO, and that's the ongoing meteorological drought in the southwestern United States. So that's something that people, especially who live out west, care a lot about. So climate models, taken at face value, don't really understand why we've seen precipitation deficits over the last few decades. The plot on the right shows the model precipitation trends over the last 30 years or so. In the dots, the observed trend is in the black line at the bottom, and then the dots are individual ensemble members. And as you can see, only one dot makes it all the way to that horizontal black line. Only one ensemble member produces the observed droughts. So again, we've either gotten very, very unlucky, or the Southwest US has gotten very unlucky over the last few decades, or there's a problem with models. Why aren't they doing this more frequently? So Western US precipitation is in part associated with the PDO, and we think there's a problem with the PDO. So we think that the force PDO, or the force component of the PDO, is too weak. Maybe that's running into precipitation there. So what if we recalibrate the force PDO and its impacts, so the precipitation field associated with the PDO, to match what we see in observations, to match the signal-to-noise ratio in observations? Well, we see that all of a sudden models do a much better job of reproducing observations. So here in the black is the observed trend of precipitation, and the raw ensemble mean is in blue. So that's just like the models taken at face value in the blue. There's almost no trend in the blue. If we recalibrate the PDO and its related precipitation pattern in the models to correct for the signal-to-noise error, statistically correct for this error, we can then calculate a new ensemble mean. I'm showing that in the orange, which matches observations pretty well. So in the raw model output, unadjusted, the decadal drought of the magnitude that we've observed happens in less than 12% of individual model runs. In the recalibrated output, this is now a median event. It occurs in about, a drought of this magnitude or larger occurs in about 47% of the recalibrated model runs. So we think that by accounting for this signal-to-noise error, all of a sudden the drought that we've seen is more like a median event, more like something we should have expected. So let's try and take that all together, and I'm running low on time, so let's go ahead and make a prediction using what we've learned, so you can all check my work in a few years. So we think that external forcing is driving the PDO, or is at least partially responsible to recent trends in the PDO, which are also associated with rainfall deficits in the south and western US. If greenhouse gas concentrations are continuing to rise, which we think they will, we think the PDO should stay in its negative phase in the near future, and therefore the southwest US will continue to experience and should be prepared for rainfall deficits to continue over the next several years and maybe next couple decades. And so that took me a long time to get to one prediction. How can we do better in the future? How can we mitigate the signal-to-noise error in climate models? So in the near term, the first thing I think we need to do is be mindful of this error and make sure that we're using large ensembles to make near-term predictions, or at least check our work against what large ensembles are saying, not using individual model runs or small ensembles. And when I say large, in the case of the PDO or the NAO, I mean very large, like 100 members, 200 members. And this seems to be necessary at least on interannual and longer timescales. Some of the prediction community is also looking at seasonal timescales where this error seems to exist too, but in response to initial conditions, not to external forcing. And so if we're mindful of this error, another thing that we can do is do what we did for the Southwest US drought, which is recalibrate this model output to try to account for this error, to try and fudge what a correct model would do and see if it can tell us anything about the future. In the longer term, I think the really obvious thing to do would be to fix climate models. So if anybody wants to do that for me, that would be awesome. It's something we're working on right now. I think we finally have some progress, so you guys will have to come back for my next talk, whenever that is, Roland. Because we do see that in new high-resolution runs, there is a reduction in the signal-to-noise error. And so that's exciting because we can finally compare models that have this error with models that have less of this error to look at what the physical causes of this, so we can hopefully correct kind of our workhorse standard resolution models. And help us build real dynamical predictions where these modes are all interacting with each other. So stay tuned, and until then, if you have any questions, let me know.
Did you show us how you do that statistical recalibration, or and I missed it, or did you not?
Oh, no. So all I did was I take each individual ensemble member and I amplify the force PDO so that the signal to noise ratio is the same as what we think it is in observations. So it's just linearly taking the PDO index in each, or the force PDO index in each run and amplifying it. And that's it. It's a pretty just straightforward linear approach. I'm happy to share the equations too.
So you could do that with a lot of model output.
Yeah, that's right. And so we've done that for like the NAO and NAO impacts too, to get Northern European precipitation and Iberian precipitation, and it works kind of the same way. So slightly different modes, slightly different signal to noise ratio. You kind of follow the same path. It's not a very efficient approach because you have to like see what the impact is associated with and scale it appropriately. But it does seem to work across different regions. Right.
Signal to noise, the next word is usually ratio.
Yeah.
And that ratio only applies for a single scalar. And so everything's been collapsed down into this time series space where all your correlations have about 2 degrees of freedom. It's either down, up, down, or up, down, up. It's like 2 degrees of freedom, time series statistics, kind of. It makes me uncomfortable. Has someone done the, so if the model were that, if the conclusion were that the force signal is too weak in models, let's not call it a signal to noise error, let's call it a signal error.
Yeah.
Okay, so you could take one ensemble member and add to it 4 or 5 times the ensemble mean force signal and treat that as observations. Mm-hmm. And then run the whole thing through your whole machinery, redefining each mode for each member of each ensemble, yada, 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 and all the way down into time series space. Do you get your same, red bar crisis, that if all you did was fluff up the forced component in one member, mm-hmm. treat it like you've treated observations, real special, and then run your whole machinery, is that it? Is that the answer? I mean, does it work? Does that explain the problem?
Yes.
That models have too small a forced component?
Yeah, so if you amplify the force component in a single ensemble member and you put it on that same plot, it ends up kind of right next to observations.
Oh, I mean way back at pattern space,
mm-hmm.
and then march it through your time series and stuff, right?
So that's
way back in pattern space.
Yeah, so that's kind of what we did for that recalibration of the precipitation field. So we also did it for SST at the same time because why not when you already have the code? Okay. So we take the pattern of precipitation for that example that's associated with the PDO in observations or in any individual ensemble member. We've done it both ways. Just amplify that pattern. Say whether that's internal, whether that's forced, we don't care. We amplify that pattern by the signal to noise ratio, so it's the same. So it's like multiplying it by 4 or 5 or 8, exactly. Depending on what you do.
And add that to one member.
Yeah, do it for every single member now, individually within each member,
Yeah.
And then we take, run it through the same machinery, take the average, and that's how we recalibrate the precipitation. So when you do that, then you get something that looks a lot like observations, as you saw just from that, quick time series, but also for the PDO.
Wouldn't it be stronger to title your whole work here, the model insensitivity error, rather than signal to noise error?
I agree. We're building on some of that prediction work that calls it the signal to noise paradox. I don't love it. They do have somewhat of a point, which I didn't totally get to, but it does seem like there is some compensation between signal and noise. When you're able to find models that have a stronger signal, there is a reduction in noise. It's small, but there is something. And so I don't know if it's right yet because we think the models are wrong. But in models that are better, there's an amplified signal and some reduction in noise that goes alongside it. So I've kept that part in just because I'm not sure that I can exclude it yet.
Quotients are a real hazard in statistics,
Yeah.
and just an asterisk.
Yeah, agreed. Yeah.
Yeah, so the amplification approach was able to replicate the trends in precipitation in like the Western U.S.
Yeah.
Have you looked at whether that like applies in generality, like in like pseudo-random like areas that the PDO affects, as opposed to like,
Yeah, so it matters most in areas where the PDO impacts are the strongest.
Yeah.
And so, I tend to think of that southwestern US because so many people live here. We live in the United States. We think of this drought as being problematic. That signal is big there. If you look at Alaskan precipitation, which is similar, just in a different area, kind of the opposite, we get the same results. It's just, not quite as sexy. It's affecting less people. Doesn't mean it's less important. We tried to do the same thing with sea surface height to see if we could learn anything about sea level rise. That seems to work, but only in the kind of far extratropics because there's still a big tropical signal there. So there's still some interaction with the tropics. We're not making the argument that the full PDO is forced. There's still a role for ENSO. We're talking about half of PDO variance on multidecadal timescales. So we do have to be a little careful about what we're saying it can explain, but it does seem to, for key PDO impacts, explain a similar amount to SST. So that's a good question. Anything else? Oh, yeah.
So your calibration that was in the smoothed time series of each of the models, is that you are on multidecadal?
Yes, that's right. I kept all of the internal variability on shorter timescales too. So I didn't touch that. I left all of the noise in there, in individual model runs. So it was just happening at multi-decadal timescales. That's right. Yeah.
Because then you could maybe calibrate it as a weighted average instead of I don't know if a simple weighted average for each model we would get the same result. And this had done before, right? So you just like some Bayesian model and then add each weight for each model instead of assuming that they have the same weight. You weight the ones that are more likely to.
Yeah.
So you could do the same way as a statistical.
I would like to do that. One of the challenges we've faced, I think you're hitting on something important. One of the challenges we've faced is there's, we looked at 12 different models here. In another paper, we have a bunch more models, but very few of them have large enough ensembles that we can be confident in our estimate of the signal to noise ratio in that model. So as we mentioned for the PDO, we think we need 100 ensemble members at a minimum to isolate it. I'm only aware of 2 models that have 100-member historically forced ensembles, so we can compare 2 members, or 2 models, but that might not be telling us too much. I'd like to have a few more. So it's hard to be confident about the weights that we should be applying these. I think that's limited us in learning what the source of this error is, because we can't find marginal improvements from one model to the next to start looking at physical mechanisms in there, other than saying, how does CDSM2 compare to the MPI model, because those two have large ensembles. So it's a little challenging. I'd love to get there if we, get some larger ensembles. That's something we're kind of working on. Is like, can we expand some existing ensembles so we can make those comparisons? So we'd like to be able to do that, but we haven't gotten there yet. Yeah.
One question. The approach I've seen in the past is that people pick out the ensemble members that look the most like the observations and then go with those. And what's the problem with that approach?
So I think there are papers that do that. They either match individual ensemble members to the ensemble mean or observations. I think what they're doing is, I think they're pretty clear about it. They're using that approach to amplify that signal. It's like you're selecting model member or ensemble members that look like observations to the ensemble mean, so that you can use less members, so you'll have a bigger signal. I think that's fine, but it's no different than what we're doing, which is just saying like, okay, well, maybe we should be multiplying this by some sort of constant. I think it's okay, but it's kind of hiding the underlying problem a little bit. It just seems to kind of skirt around it by selecting on the dependent variable a little bit there. I'm thinking of like the Smith et al. 2020 paper about the NAO, where they do that. A bunch of the Met Office people do that. They pick their initialized predictions that are closest to either observations or the ensemble mean and say, we're just going to use our like best 8 ensemble members. And all I think that's doing is letting them have a bigger amplitude response, because they're picking ones that already match the ensemble mean.
But you could predict the continuing drought in Southwest U.S. more cheaply that way, couldn't you? Or
at least in the papers I've seen, they still have to have a large ensemble to be able to pick the ones that are best.
all
All right, let's thank Jeremy again.